production. Hi, everyone. Thanks for listening in today. As Phil mentioned, today I'll be talking about PSM3, specifically giving a brief update on the capabilities and the architecture. I'd like to acknowledge my co-author for this talk is Todd Rimmer, who's unable to join today. So I'll be fielding all the difficult questions. A brief agenda of the talk. First, we'll start with what is PSM3. I will talk about PSM3 integration with OneAPI. I'll talk a little bit about the evolution of the PSM3 architecture and then talk about the new capabilities that exist in PSM3 since our talk last year. I'll have a slide that shows the use of PSM3 with Nickel and an AI training benchmark therein. And then wrap up with some slides showing the performance of PSM3 for the features that we've been discussing today. So PSM3 is an existing libfabric provider. It leverages concepts and codes from the OmniPath architecture, largely known as PSM version 2. Therefore, it's mature and feature-rich. It's really stood the test of time with performance analysis and tuning, as well as bug fixes and robustness. The key difference with PSM3 is that it's designed for Ethernet. It optimizes performance and scalability of Ethernet in HPC and AI. It's based on using standard RoCE v2 protocols and APIs. A key change to our recent deliveries of PSM3 is that it now also supports sockets TCP IP. PSM3 is available now. You can get the latest version upstream. Now there's two ways to get the version. It's integrated into libfabric and selected Linux distros, but we also release PSM3 in our software suite known as Intel Ethernet Fabric Suite, which we have on the Intel Download Center. There's also various out-of-tree code for older distros available that you can pick up on GitHub. Here is a high-level view of the OneAPI software stack showing where PSM3 fits into the big picture. If we start at the top, color-coded in yellow, where we have, the consumer, the user of this technology, they're writing applications or AI frameworks. Following down the various levels of the stack, try not to pay too close attention to the relative widths or overlap of each one of these levels. The key point here is that there's a lot of different components and recipes available to get down to the low-level hardware. What we're focusing on today is, the OneAPI implementation in orange, and then on the far right, the communication stack portion of that, where we integrate with libfabric, and we are a provider into the libfabric OFI. And we have PSM3 sitting down here, which allows us to interface between the kernel drivers. Specifically, we'll be showing the Intel RDMA driver to get RoCE v2 capability on Intel Ethernet NICs, and then eventually the hardware down below. So this is a view of the previous PSM3 architecture. I'll just go through this briefly. Again, at the top, we have the API that's exposed to the user, which is the OFI interface, where we hook in with our PSM3 provider. PSM3 has, various methodologies for messaging. Our major functions include endpoint and connection management, matched queues, active messaging, and then info queries, which allow OFI to query data about the hardware. We have various messaging paths, such as the interconnect protocol stack, shared memory, self-communications, and then we support the common wire protocols, tiny messages, eager, and rendezvous that have been discussed. For the rendezvous module, we actually have, as part of our Ethernet Fabric Suite, we have a kernel module which is down here, the RV module. This is purpose-built to enable RCQ pairs for the highest performance point-to-point communication, where we can achieve line rate on 100 and 200 gigabit networks with a single MPI process. Scattered throughout here on the right are various types of capabilities in terms of logging, data type management, statistics monitoring, and various timers associated with robustness and retries and things of that nature. So if you focus on the bottom, as I switch to the next slide, you'll see where we added the capability of our TCP IP handling. So we have this new socket interface in our HAL layer, which primarily is used right now for TCP IP, but we also have UDP support in there as well. So a brief overview of the new capabilities. We do have a runtime selection of RDMA or TCP IP. So if you want to run over an RDMA capable network, you would specify the verbs HAL layer and specify the NIC in terms of an RDMA device. Or if you want to run over a TCP network, you would simply specify the NIC name in terms of the netdev, and PSM3 detects which one it wants to use and follows the appropriate path. We do support IPv6 and v4 addressing for both Rocky and TCP. And then we also have runtime NIC filtering controls. So this becomes very important when you have clusters with many different types of networks. Oftentimes largely found in benchmarking clusters, but also, if you have various types of network technologies and you want to run PSM3 over different networks that are available, we can filter those NICs in terms of wildcards, subnets, address formats, or even NIC speed. And then we have ongoing tuning and validation with CPUs and GPUs, which I'll be showing a little bit of that today in the performance section. So here's an example of PSM3 NIC filtering and showing our multi-rail capability to distribute traffic across the available NICs. On the left-hand side, I have a simplified schematic of an HPC server, which might have a few different connections into a couple different networks. In this example, we have two Ethernet NICs connected to a primary network of interest, which we'll call network 1 in green. And then we have another NIC connected to a secondary network, which we don't particularly want to run traffic over for whatever reason. This is a scenario where we can use wildcards in PSM3 to select just the two NICs of interest. So in the green box down here, when we run our MPI job, we would simply enable the environment variable PSM3 NIC and select the verbs device name in terms of a wildcarded format. In this case, we just want to use RDMA 0 and 1. And then we'll also implement a feature known as multi-rail, which will tell PSM to stripe the traffic across the available NICs that we have selected. So in this case, we're going to be striping messages across the IRDMA 0 and IRDMA 1 device. This multi-rail flag is actually from the perspective of a single MPI rank. So you can still run dual rail or 4 or 8 rail configurations with multi-rail equal to 0. It's just that each rank will use a dedicated NIC in the fabric instead of the striping behavior. On the right, I'm showing example performance measured in this configuration on some Xeon 8360Y Ice Lake servers using Intel Ethernet NICs. And we're running a uniband and biband benchmark. So this is the Intel MPI benchmarks, unidirectional streaming and bidirectional streaming benchmark using these two NICs. So this is a benchmark that just uses one process per node. And you can see with this multi-rail capability allows us to achieve line rate for both of the NICs in both unidirectional and a bidirectional message pattern. This slide shows our recent enhancements with incorporating PSM3 with NCCL. So we do take advantage of the AWS OFI NCCL plugin. It now supports PSM3 with GPU Direct. There have been a few commits over the recent few months which help enable this technology over PSM3 with Ethernet. On the left here, we're showing a slightly different stack than what we showed in the previous slide with OneAPI. Here we're showing this, GPU nickel capable stack where in the green are software stacks provided by third parties. The black is what you would get in the distribution, and then the blue is what we're providing from Intel. And you can see really where we plug in is under this lib fabric layer where we inject our PSM3 provider, and we're able to operate these applications which function just fine over lib fabric and nickel, except that now we're using Rocky in the network level. So here's an example of a benchmark on a small internal cluster we have to demonstrate this capability. So this is an AI training workload TensorFlow 2.6 with Horovod using ResNet 50. And this is a 4-node cluster with NVIDIA V100s. We do have A100s as well, which I'll be showing some performance from on the next slide. But this shows the scalability of this technology going from 1 GPU up to 4 nodes with 4 GPUs, and the difference between the performance if we run with PSM3 over Ethernet without nickel, which is in the solid black line, and if we incorporate nickel in the solution, we get a pretty significant performance bump and see about 90% scaling efficiency with PSM3 when we're using nickel. This slide shows our lower level performance using GPU buffers with PSM3. So these data are measured on nodes which have NVIDIA A100 GPUs, and they're on servers with PCI switches. So we really expect the best GPU direct performance because both the GPU and the NIC are connected to the same PCI switch, and we don't get the CPU bus involved during the transfers. Showing latency, OSU latency on the left, unidirectional bandwidth in the center, and bidirectional bandwidth on the right. The black line shows what the performance is if we do not use GPU Direct. So we have the host buffer copies, and you can see the latency is about 20 microseconds without GPU Direct. As we enable GPU Direct, we get a pretty competitive latency of around 8.8 microseconds on these systems. For unidirectional bandwidth, you can see that we saturate line rate quite nicely with GPU Direct enabled, whereas with GPU Direct not enabled, we're not quite able to reach line rate. And then the same with bidirectional bandwidth. We get a very nice saturation of bidirectional bandwidth with GPU Direct enabled with PSM3. So these data were measured on these systems, which are Gen 4 systems, with a single 100 gigabit Intel Ethernet NIC and the A100 GPU. The last performance slide I have shows the relative performance of PSM3 with our TCP support versus our PSM3 with Rocky. So this is a PSM3 only slide, and what we're showing is for various applications that we test internally, what the difference in performance is between our TCP and our Rocky stack. Two key points to this slide. One is that the TCP implementation is very stable and robust, and it runs on every application we've tried. Our first few development builds, we worked out some bugs, and now it's stable on every application that we run internally that runs over Rocky. And the second key point of this slide is that some applications will perform just fine with TCP. And others will greatly benefit from Rocky. So the applications on the left here are ones that are more latency sensitive and actually, are impacted by the TCP stack more so than the applications on the right that we've tested at this scale. So I'll wrap up with some conclusions and future work. PSM3 is robust and it's a proven leap fabric provider, and it's purpose-built for HPC on Ethernet. It works with existing HPC and AI apps, as well as other RDMA and verbs capable networks. It also now supports nickel as well as TCP IP. In the future, we're going to be continuing to tune for HPC and AI apps. We have a few different new clusters that we are working with that have, many NICs per node, and we're working on improving integration with OneAPI and OneCCL for multi-rail performance and as well as portability of the codes. That's all for my talk. I have an eye chart here for configurations, and at this time, I'd be happy to answer any questions.
Well, thank you. We have one question queued up, and the question is, did you make any progress to upstream the RV kernel module? The questioner recalls that the RFC got shut down.
I am not aware of the latest status of that. I do believe our kernel module is on GitHub, but I'm not aware if we have been able to upstream the kernel module yet.
So you've got a few moments. Is there any of the slides that you teased up in the backup slides that you'd like to show?
Unfortunately, I don't think I have any backup slides. No, that was all that I had planned to share today. So
fair enough. Thank you very much.
And I think I just realized that I did not have my video on, or do I?
You don't have your video on. You're showing your slides, but your video.
My apologies for that. I neglected to turn on my video, but I promise I'm sitting here paying attention.
Are there any other questions? Okay, I don't have any questions queued up for you. Thank you so much.
All right, thank you.